In the last class, we were formulating some strategies of obtaining bond graphs for circuits in a sort of generalized way. And we say that one of the ways of doing it would be if we can identify the nodes in the circuit, and those nodes, since anything connected to the nodes will share the same effort. So, those nodes will be designated the junction 0, and then anything connected between the nodes will have to share the same current, and so they will be connected by a one junction, which means that this is a different way of looking at it. So far we were doing it by logic, we are looking at the what are connected in series and what are connected in parallel, accordingly we are laying out the junction strategy, but now it is a sort of blind procedure that we are talking about. Why is it necessary? In the example that we showed in the last class, it is not very evident, but let me tell you that there are situations where it becomes somewhat difficult to figure out the series and parallelness. For example, take this circuit. So, this is a source of effort. Now, in this case, can you see what is connected in series and what is connected in parallel? It is not immediately evident. And in such cases, and if such a thing is part of a larger network of elements, it becomes difficult to figure out how to connect these series and parallels. So, in that case, it will be convenient to go by that procedure. So, we can identify in this circuit at least a few nodes. This will be a node, this will be a node, this will be a node, and this will be a node, right. So, we will say that these are the 4 nodes, these are the 4 nodes, will designate by 0. In between, this is connected, so we will connect them by 1, and what is connected to it? An I element. In between these two, there is a capacitor, so that is connected in series between these two, that will be our line of logic, and that is connected by a I element. Similarly, here it will be a one junction connected here, and here it will be a C element, here it will be another one junction, and you have I element here. Apart from this, there is this thing, so we will have to connect it like this. This is what? It will again have to be connected by a one junction, and what is connected here? A SE. So, that is the representation of the circuit now. But then I said that one of these junctions will have to be, in order to, what have I missed? Oh, there is a resistor, yes, there is a resistor. So, here it is a one junction and connected a resistor. So, that is the complete circuit. Now, we need to reduce this, and the way of reducing would be, as I told you, that out of these different nodes, one would be assumed to be at the 0 potential, grounded. So, let us assume, say, this is grounded. The moment you do that, you will effectively say that here is an AC element connected, which is equal to 0. The moment you do that, this bond carries 0 power, because the effort is 0, and since this is a 0 junction, therefore, the same effort is distributed, equalized. So, all these bonds will carry 0 power, and therefore, they would be unnecessary. Okay. So, this whole thing is unnecessary. Now, the moment you do that, you find that this becomes a through junction. So, whatever are the efforts and flows in this bond will be the same as the efforts and flows in this bond, and therefore, this one junction is unnecessary. So, we can then connect it through. Similarly, here through. Similarly, here this is not there. So, this can be a direct connection. So, all these will go, and we can say here is AC element connected. Okay. Can there be any further reduction? Can there be any further reduction? No. Okay. So, we have this situation, but it looks ugly. So, let us lay it out in a more handsome fashion. Can you see the whole thing? Yes. Let us try to lay it out in a more handsome fashion. You have the this 0 is out, right. So, you have 0 1 0 1 0 1. So, we can do it this way. Let us start from here. 0 1 0 1 0 1 0. Can you see that? It forms such a loop. With this 0, what is connected? The I. With this 1, what is connected? C. With this 0, what is connected? S E. With this 1, what is connected? I. With this 0, what is connected? C. So, I will remove it because then I will not be able to draw C. And with this 1, what is connected? R. Okay. A pretty handsome arrangement. This definitely could not be seen from the original circuit. We could arrive at that only because we followed this procedure. Now, let us do the usual things in order to practice. One, we will have to put the power directions, which will be like this, this. Now, you would notice that these bond to bond ones, you could put any direction of power. So, we will arbitrarily put it. It is natural that if the power comes here, it will go in these two directions, but after that it is not clear. Nevertheless, we will put it like that. Remember, these are arbitrary. You could as well give the opposite direction. It will only mean that the positive and negative would be in the different direction. Let us put the causalities. Start with SE. Its causality is like this. It gives the effort information and receives the flow information. This fellow I element, its natural causality is like this. The moment it gives the flow information into the one junction, the flow information must be taken out, right. So, now this 0 junction has received the effort information, and that is why it must distribute the effort information like this. Okay. So, it gives the effort information in this direction and receives the flow information in this direction. As yet these are not causal. So, let me put the causality here. See, its integral causality is like this. So, it is giving the effort information into the 0 junction. The moment it gives, it has to be distributed like this. R will leave out to do later. See, what kind of causality does it have? Its natural causality is like this. So, as yet these two fellows are taking out the flow information, therefore, this bond must bring in the flow information like this. So, in this 0 junction, as yet the causal structure is not complete. So, we will put it here. This is the natural causality of the I element. So, it has taken out the effort information, this one has brought in the effort information, 0 junction. So, this has to take out the effort information. 1 junction, both these are taking out the flow information, and therefore, this fellow must be giving the flow information. Okay? Then it is done. Okay? So, that is the causal structure, and then you put the numbers. So, this way we can easily obtain, by this sort of algorithmic procedure, we can easily obtain the bond graph for any given electrical circuit. What will the equivalent be in mechanical systems? Suppose you argue that okay, for electrical systems we understand, because we can identify nodes. In mechanical system, what we will do? See, we started by identifying the nodes, because in an electrical circuit it is easier to identify the different voltage points. In a mechanical system, it will be easier to identify the different velocity points, right, because the masses move with velocities and you can identify. So, in mechanical system we will take the opposite view. We will first identify the points that have different velocities, and the moment you have something at different velocity, something at a particular velocity, something must be sharing that velocity, connect that with the one junction. Now, wherever there are springs or friction elements, the two sides share the same effort. So, those things you connect by a 0 junction. Simple logic, just the opposite of what we did in the electrical circuits. Let us see an example. Let us start with an example that we have already done, the way we did for electrical circuits. For example, this is something that we already did. Mechanical system with this connected to the ground with some force acting on it. Fine, this is what we did earlier. A system with a mass, spring damper arrangement connected to the ground with a force acting on it, and this is a lever with A B ratio, and here is another mass M2. So, this is M1, this is M2. Earlier we went by logic, but now let us go by this procedure. What are the different velocity points? 1, I can easily see. So, we will put a 1 junction here. 2, so we will put another 1 junction here. 3, we will put another 1 junction here. 4, that is also another velocity point, another 1 junction here. Done? Fine. Now, what is connected to this 1 junction? The mass, definitely. So, we will connect the mass to it, I element. This force also shares the same velocity. So, that will also be connected by means of the same 1 junction, right. This is the f of t. But now, these two fellows are there in between these two 1 junctions, and they have to be connected by 0 junctions, because their sides share the same effort. So, we will connect a 0 junction like this and connect this is the C element. We will connect another 0 junction and connect the R element. All right. Now, here we have between this point and that point, we have the lever. So, between this 1 junction and this 1 junction, we will have no transformer. Yeah, it is a transformer, TF connecting. Now, between this point and that point, we have a 0 to C, and this one junction is connected to this I. Okay. There is something more. Here there is a ground, something that does not move. How do we represent that? No, it is SF. It is a source of flow which is forcibly equal to 0. So, that is connected to SF. Okay. Now, this SF being equal to 0 will immediately mean that this bond carries no power. That will mean, since this is a one junction, will mean that this and that, these two bonds carry no power. So, we will eliminate this. As a result, this becomes a through bond, we can connect directly. This becomes a through bond, we can connect directly. Can you reduce anywhere here? Here we can connect directly, it is not necessary. Here we can connect directly, it is not necessary. Right. So, we have a far shorter bond graph now. Let us see, let us start with this one connected to SE I C R transformer, and then it is, this is not necessary, to a 0 junction connected to a C and I. That becomes the bond graph. Okay. So, that is the simple logical procedure by which you can write the bond graphs. Clear? Now, just as a matter of practice, put the power directions and the causalities. Here there is a AC, so it is like this is done. Power directions were simple. Causalities, how do you put the causalities? First, let us start from here. AC will take flow information, I will give flow information. The moment you give flow information into the one junction, all the others must take it away. So, the C element is properly causaled, TF will take it the other side, 0. So, let us start with the C element. C element will have this causality, it is bringing in the effort information, naturally it has to give the flow information, effort information to the other things. So, it is done. Okay. Good. Let us handle now a relatively more complicated problem. In this problem, we will consider, imagine there is a car, and as this car, okay, I will not draw the wheels, because the wheels are actually suspended, the car is suspended on the wheels by means of a suspension, which is nothing but a spring damper arrangement. Okay. So, it will be good to see this as a connection where you have a spring damper to something. Here also it is, we will just draw it this way in order to make the physical property salient. Now, what is there at the bottom? Bumpy ground, a road which is normally bumpy. That means, as this fellow goes ahead, and if the road is bumpy, what is seen at these 2 points? Source of flow. Yes, source of flow, which is sort of imposed on these 2 points by the character of the ground. So, at these points you have source of flow. So, imagine that you have a bumpy ground here. Okay. We are not considering the forward motion, we are considering the up and down motion, but notice that there will not only be one up and down motion, the fellow will also rock. That means, sometime the front will go up, sometime the back will go up. So, there will be some rotational motion also. So, how to do this? The points of suspension, if you put this, and there would be some point at which the CG resides, say here. So, the CG is here, then the CG is at some distance A from here and B from here, visible. So, depending on that, here is the CG and here are the forces acting. Because of this, it will be going up and down, fine. And not only that, the CG itself will go up and down. So, one will be the rocking motion, the other will be the total up and down motion. And for the rocking motion, you will have to consider the moment of inertia. For the up and down motion, you will have to consider the mass. Now, how to make the bond graph of this? First, identify the velocity points. Where are the velocity points? 1, 2, direct. So, let us start with this 1, 2. Velocity points will be one junction. So, there will be one junction here corresponding to this, another one junction here corresponding to that. There will be one junction here, another one junction here. These two are also the velocity points. So, one here, one here. Now, this motion, the car's motion, will have two components, one the rotational component, another the translational component, and these two are also velocities, different velocities. So, for that we will put two one junctions like this. We will see what we can do with it, but we can identify there will be one junctions, right. Okay. Now, what are connected to these two? We have already understood that these are connected to SF, source of flow. These are connected to SF. Okay. Now, in between this and that, this point and this point, you have the spring damper arrangement, whose representation we already know. It will be right. So, this will be like this. No problem. Okay. Now, how to connect this point and this point and this point and this point. This point, it's this one junction, whatever bond is connected to it will have the velocity here. Whatever bond is connected to this one will have the velocity here, up and down velocity. Now, if this fellow is going up with some velocity, this fellow is going up with some velocity, how is the total CG determined? How will it be given? How will that be given? And if this is moving at some velocity, if this is moving at some velocity, how will the rocking motion be given? Try to understand these 2 points. Notice that from here it is giving not only it is giving a force to the car, right. Here is a force being applied, and this force is causing these motions, right. So, you are giving a force to the mass that is causing the motion, fine. So, in order to have the force effort, what we will do is we will connect it by a zero junction, so that at this point what we have it, what are these? These will have the force that is acting on this, Now, if a force is acting here, another force is acting here, what will determine this up and down motion? The addition of the two forces, will ultimately cause this motion. Which kind of junction causes the addition of two forces? One junction. One junction is a flow equalizing junction, but the effort summing junction. So, if you connect it like this point and this point, here the effort that will be seen is a summation of these two efforts, fine, and what will be connected to it? It will be the I, the mass. Done. Now, this is related to the rocking motion. The rocking motion, suppose you have applied a force here, you have applied another force here, what creates the rocking motion? No, not the difference. Yes, it is a moment. Yes. So, this one, if there is a force applied, times A will be the moment, the force applied times B will be the moment, and so the torque felt by this CG will be yes, but in that case, when we are talking about at this point the torque being applied, the torque is, or the moment is, how will you see that, this one and that one? Suppose the motion in the counterclockwise direction is assumed positive, then this fellow will try to move it that direction, and this fellow will try to move it in the opposite direction. Okay. So, they will act in opposite ways. So, it will be see, in that case what it means is that whatever is the effort here, is the effort means force, that will be applied to this junction through a transformer, right, because the force will be converted into a moment and thereby it will be applied. So, it will be a transformer connected to this, here also there will be a transformer connected to this, and the transformer ratios will be one into B and minus A. So, this side will be B and this side will be minus A. Okay. And what have you got here? The total, in that case, after summing these two torques, what you have here is the total torque applied, and that will be connected, that will be causing the motion in that direction. This will be a I element, which is be the inertia, moment of inertia. Is it right? Is this B or 1 by B? It will be multiplied by B to give the torque. Yes, right, done. Fine. So, you have this, can we reduce it? No, there is no zero velocity point. So, we cannot reduce it. So, this is the bond graph, just causal it. Put the power directions first. And then the interbond ones we can, interjunction bonds we can anyway do it. Causalities, SF will give this, SF will give flow, one junction it will equalize, one junction it will distribute the flow. C, natural causality is this, the moment you have it, it has brought in the effort information, it must give out the effort information. Similarly, here what does the R do? As yet you do not know. So, let us start from the other side. Here it is a I element, here it is an I element. So, integral causality is one junction. So, it will distribute. Transformer, it will take out the information. So, this 0 junction has received both the flow informations and distributed the effort information. So, the effort information must be coming from this bond like this. Here also it will be like this. Here is a one junction where the flow information has come, and therefore, it should distribute the flow information. Has come, should distribute. This junction is now bringing in the flow information and taking out the effort, therefore, the R must produce the effort information like this. Done. Okay. So, even this kind of relatively complicated things which have two different types of motion in the same body, we can represent like this. And in fact, if you obtain the differential equations from this, if you simulate this, you can easily obtain how a specific car is going to bounce. And this is actually done. These things are actually done in industry in order to find out how should these things be tuned, so that there is a least amount of bumpiness. Okay, so we have understood how to obtain the bond graphs of relatively complicated circuits. Notice that there are things that repeatedly appear. For example, this combination that repeatedly appears. You will see later that this combination, the whole thing can be abbreviated. This spring damper arrangement as a sort of cushion is a unit that can be abbreviated with one bond going up and one bond going down. So that later all these things can be just put as one element, but that comes later. First you have to understand this, but then you will see that there are many things that come as an unit, and that unit has a specific characteristic that are given by two extremity bonds. Fine. Now, there are some situations where we run into some difficulties when writing the differential equations. Why? Or giving the causal strokes. See, what we did, I was all the time giving you practice in putting the causalities. Why? Because that is where people often make mistake. But then all these were sort of straightforward, there was no difficulty. But let us illustrate a situation where you do have difficulty. Suppose there is a circuit something like this. A simple circuit that does not show any sign of being difficult. No difficulty with the circuit, you can easily connect it. Now, let us draw the bond graph of it. SE connected to I, connected to R, in parallel with I. Here it is a series arrangement of R and C. Okay. Fine. So, give the power directions, which would be somewhat simple. Now, start giving the causalities. SE element will give the flow effort information to the rest of the system. So, the causal stroke should be here. As yet this value is not determined. So, let us go straight to the I element. I element's natural causality would be like this. It has brought in the flow information into the 0 junction, but as yet the other bonds will not be determined. So, let us do it here. C, the C element has brought in the flow effort information and taken out the flow information, all right, but this is a one junction. So, as yet these things are not determined. How will you complete it? In order to complete it, you might argue that okay, let us what is the problem? The problem is that this one junction does not yet know where the effort flow information is coming from. Let it come from here. Suppose, what does it mean? It will immediately make this one complete, because this has to take out the flow information. The moment this one has taken in the flow information and taken out the effort, this bond must bring in the effort. So, it has to be like this, right. So, this is the one junction in which the flow information has come, and it must be like this, done. But notice that you had to somewhat out of your hat put this causality. Another fellow can say that no, I do not want to put the causality here, let us start from here. Let us see, let us do it here again. SE to an I to R to 0 to 1 to R I C. Now, the ones that we know already, let us put, and now that fellow said that okay, let us start from here. Now, this one junction needs the flow information in order to be complete. So, let us do it like this. So, that this fellow brings in the flow information. The moment it has brought in, it has got it. So, it has to distribute like this. So, this 0 junction, it has taken out the effort information, therefore, this bond must bring in the effort information like this. So, the flow information has gone, one junction, it must distribute, again completed. But you see, this and that both are true, but they are differently causal. What does it physically mean? What it physically means, if you try to understand that, let us obtain the differential equation starting from this, starting from this premise. We either have to choose this or that in order to obtain the differential equation. Let us choose this one. So, let us number them first. It will be 1, 2, 3, 4, 5, 6, 7. So, based on this, we are about to write the differential equation. So, let me place it here so that you can see. Can you see? Visible? Yes, we have some workspace here then. So, we first start it by asking the first question, which is what do the elements give to the system. So, the answer to that question with respect to the AC element would be SE1 would be, what does it give to the system? E. So, E1 is equal to the E1 is this E R1 R2 L C. Okay. Now, next is R2. So, R2 gives what? Okay, let us do it first with the storage elements. So, I4, what does it give to the system? What does it give to the system? F4 is equal to P4 by L. Okay, done. Next question is asked to this element C7. What does it give to the system? E7, which is Q7 by C, right. The next question is then we start asking the question to the resistances. So, R2, what does it give to the system? F2, right. F2 is E2 by R1. Now, where does the E2 information come from? E2 would be this and that. So, it will be E1 minus E3 is equal to E1 minus E3 by R1. E1 is known, E3. E3, where does it come from? Yes, that is a strong bond. So, is equal to, okay, let me put R1 by R1. This is known, E1 is known, minus E5. So, E5 is the one that has brought in that information. E5 is obtained from where? Yeah, yes. So, is equal to 1 by R1 E minus E6 plus E7. So, this will minus. Now, E7 is known, Q7 by C, but E6 we do not know it yet. Keep it like this, fine. So, presently keep it like this. Now, let us ask this question to R6. So, R6, what does it give to the system? E6. So, E6 is equal to R2 F6. F6 comes from F5, R2 F5. F5 comes from F3 minus F4, yes, is equal to R2 F3 minus F4 is known, P4 by L. F3 comes from F2 is equal to F2. So, R2 F2 minus P4 by L. So, you see you have landed up with one equation where the left hand side is F2 and you have E6 in the right hand side, and another equation in which E6 in the right and F2 in the left in F2 in the right, which means that in order to obtain F2 you need E6, and in order to obtain E6 you need F2. This problem is called a algebraic loop. Can you see that it has run into a loop, logical loop? In order to know this, you need to know this. In order to know this, you need to know this. So, this is called an algebraic loop. And whenever there is a indeterminacy of the causal structure, so that you are having to, I mean, out of your hat put a causality in one of the R elements, it immediately indicates that you will have this kind of problem while obtaining the differential equation. But you would notice that that is not a big deal. Why? Because you have two equations and two unknowns, right. The moment you have two equations, two unknowns, you can always solve it and obtain these two individually. So, they are actually determinable, no problem, but you have this causal loop. So, how do you obtain this? Can you just do this bit of algebra to obtain this individually? will require a small bit of algebra. I think it will be F2 is equal to 1 by 1 plus R2 E minus and E6 is equal to check that. So, all we have done is using these two, here is a quantity, here is a quantity, and here is a quantity, here is a quantity. We have simply solved the two equation to a unknown problem in order to obtain this individually. Obtainable. So, then the rest of the problem can be done exactly the way we have learned. So, after we have obtained the equation, the answers to the first question, then we will ask the second question, namely what do the two integrally causal storage elements receive from the system, and we will go exactly the same way. I will leave this exercise to you. Okay. Fine. So far we were considering the R element, C element, I element as a one port element like this, I connected to the rest of the system. What does it mean? Means that here is a, say this is bond number 1, it is a E flowing and this F flowing, then this E and F completely determine the characteristic of the I element, which means its effort is completely given by the history of its flow. So, that is the character of the I element, that the voltage is equal to L di dt, or I flow is integral of the effort. So, the flow now is completely given by the history of the effort in this bond itself. But there are situations where the flow could be given by the effort not only in this bond, but in another bond also. Where? Imagine the situation of a mutual inductance. Take a circuit, say you have got a source and you have got an inductor and you have got a resistor here and this is another inductor here, something here, and imagine that there is a coupling between this. So, this L1, this L2, R, C, E. Now, how we will do? If you try to obtain the bond graph directly, you will say that okay, if I ignore this M part, what we will do? We will do it simply like this. No, I will do it here. SE in series with an L1 I colon L1 in parallel with R in series with 1, it is a I L2 and C. If this inductor in this mutual coupling were not present, this would be the diagram. Okay. But the moment the mutual coupling is there, what happens? Then the voltage induced here will be dependent not only on the current here, but also on the current here, right. So, the current here is available at this one junction, the current here is available in this one junction. So, some way these two will have to be coupled. Coupled how? this how question, how are the momentums and flows are coupled. In order to probe that, just let us just get back to the question of the kinetic energy of this whole system. Kinetic energy T was, how will you write it, half L1 Q1 dot square plus half L2 Q2 dot square plus M Q1 dot Q2 dot. Okay. So, your momentum P1 was the derivative of T, or derivative Lagrangian is the same as in this case T, and derivative with respect to Q1 dot. This will come to be L1 Q1 dot plus M Q2 dot. Okay. Similarly, P2 will be it is M Q1 dot plus L2 Q2 dot, right. So, how are the momenta and the flows, these are the flows, right, and the flows related? You would notice that you would be able to write a matrix equation P1 P2 is equal to L1 M L2 Q1 dot Q2 dot, right. If this were not there, then how would you write the equation? In that case, if you only consider one inductance, how would you write? You would write P is equal to flow by L, that is all. No, Li, so L into flow. So, in this case, the momentum is just this number times the flow in the same, that is why it can be represented by one bond. But here you see they become coupled in this matrix way. Now, this is the flow in this particular junction, this is the flow in this particular junction, and therefore, these two will have to be coupled by means of these two matrix in order to obtain the character of this. So, the way to do that is, I will start from here and do it. SE 2 1 2 0 2 1 R C. Now, here can you see that? Can you see the whole of this? Yes. This particular thing is available here. This is F1, F here, flow. This is available here, the flow. So, these two will have to be coupled to, this is also having the character of the inductance. This whole thing is also having the character of a momentum. Why? Because in a momentum, this is how they are related. This is a momentum like thing. So, it will also be an I element, sorry, it will also be an I element, but its character will be represented by a matrix L1 M L2. That completes the story. These are two port I element. Under such situations, you will have an I element with two ports. Okay. Is the concept understood? Why you need a two port I element sometimes? These are also called fields. So, this is a I field. I field means a two port I element. That is a natural necessity when you want to represent a mutual inductance. There will be situations where you will need similar representations for C, for R, things like that. And in the next class, I will illustrate under what condition you would need that. Fine. Okay, that is all for today.